So in 7.6, what we're going to do is we're going to take a look at quadratic functions now. Now, we've already looked at parabolas in vertex form. And if we just write f of x instead of y, we start talking about functions and what functions are. But we're going to look at two different types. We're going to look at them in standard form and in vertex form here. And then what we're going to do is we're going to talk about things called extrema. What does it mean for something to be very extreme? If someone's an extremist. What does it mean to be extreme?
Like they go to far distances, like for example.
Yeah, they don't stop. They go over the top, right? In extrema, or an extrema really, in math, on a graph, anybody have a guess as to what an extrema would be? There are two types of extrema. I'll give you that hint.
The highest point or something?
The heights what?
Like the two highest points.
Okay, you're on the right track. You're a little bit off though.
The highest and lowest points.
The highest or the lowest. An extrema is a minimum or a maximum value on a graph. So part of this lesson is going to be to determine what the extrema are. Is it a minimum? Is it a maximum? It depends on if it opens up, or opens down. And we're going to look at word problems where we want to maximize something. So say you want to maximize the profit made from a certain manufacturing industry that you might be in. You'd have to find the minimum or the maximum value along the profit graph or the profit curve. And you're going to see that later on in AP Calc, and Nick, you can testify to this. You're going to use calculus methods where you're going to take derivatives, set them equal to 0, and you're going to be able to find those mins and maxes a lot easier. And the whole idea is about optimization. So if you were in industry, and say you want to, come out with a new product. Let's think about something. I was talking to somebody the other day about backpacks. About backpacks that can store and generate energy. Have you heard of this before? So imagine you're walking on a college campus, and you have a really hilly campus. Your backpack is constantly sagging on your back. It kind of bumps a little bit. If you put a mechanism in there that could have some sort of electric charge moving across plates, it can generate power, and then you can store that power. You can store that power on a battery. And then you can plug something into that battery and charge like a phone in your backpack as you're walking around. So imagine you wanted to sell this product, and what you wanted to do is you wanted to say, all right, we need to look at a manufacturing industry. We want to keep it American. We want to minimize our costs. So we have to figure out what is our cost function, or what is our profit function, or what is our cost versus revenue. So how much money is going out, how much money is coming in. You can plot this as a function of the amount of products you make. So usually N is your independent variable here. So you might say, for the first 5,000 products we make, we can see that our profit function follows a linear curve. But then as we make more and more of them, it starts to grow at a faster rate, more exponential or maybe parabolic. We start making more profit as we make a lot more of these items. Because we recognize that we're only losing a few cents on each item, so let's make a lot of them, and we'll make even more money in the end. So you can plot a graph of that, but there might come a point where, you have only so many resources available, right? So you can't make too many products. Everybody knows there's got to be a limitation, even for companies like Apple. What happens when you want to buy an iPhone in the beginning? What do they always have to have? There's always a problem at the very beginning when the new iPhone comes out.
They always run out.
Yeah, they always run out. There's never enough in that first few weeks of an iPhone. There's always a point where they run out and it's on backorder. And you have to wait maybe a week or two to get a new shipment. So every company has its limitations. So what happens in your profit graph is that it starts to fall off now. Because if you make too many items, you start to lose money because your resources aren't there, or maybe, the machine that you're using, this assembly line process, has limitations to itself. So if you start running these items too fast, what's going to happen as they move along the process line? What will happen eventually? You might run into what?
Resources.
Yeah, lack of resources, or maybe the conveyor belts are running too fast, or what might happen in the machine.
What if like the demand for the product goes down? Because just so many people have it and not many people want it anymore.
If the demand goes down, you would obviously lower the rate in which you're producing them also. But you would want the demand to be up. But this curve we're looking at right now, it is inherently a function of demand, for sure. And it's a function of how much supply you have coming in, and those are your resources, really. But if we're just looking at a profit graph, what I'm getting at is that as you go beyond a certain value, the machines might start to break down. You might need more resources than are available at your hand, or labor might be increased in value. Maybe you're able to get labor where your labor is, a little bit above minimum wage, you can help to produce anything more. And, there's companies like, and it's a terrible thing, but it is true, there are companies out there that they minimize the amount of hours a company might be able to give to a certain employee so that they don't have to pay them any benefits. So what they'll do is they'll say, we're going to cap your hours this week at 35 hours a week for employees. Benefits for a company might cost $15,000 a year for health insurance, for all that stuff. So if they can keep all their employees under a certain amount of hours, they don't pay them those benefits. It's a really terrible thing to think about. It's really like sleazy. It's trying to be, it's been regulated more and more by the government that companies can't do stuff like this, but they still do get away with it. And as a result, what do? They save a lot of money. So suddenly, if they have more products, they need to give more hours to their employees, which pushes those employees over the 40-hour limit. They become a full-time employee. Now they're losing $15,000 per employee for that. So as a result, you have these weird variations in your curve. It's not going to necessarily be just parabolic, but the concepts that we're going to learn in this section, where you're finding maxes and mins on parabolic graphs, are the same as the functions you would look at where they might be like fifth order, where there's several mins and maxes along the curve, where they're not necessarily perfectly symmetric, where in parabolas they are, which makes it easier for us to do this. But when they're not perfectly symmetric, you can't solve these this way. You need to go to calculus and understand those ways to solve, to do that. Okay, so I know it's a long intro, but this is really one of those important sections of the year, like I keep talking about, where you're going to see this over and over again. You're going to see it next year as well. You're going to look at rates of change in mins and maxes for those graphs also. All right, so we have two forms we're going to look at. The first of the two we're going to call standard form. And when we're looking at standard form here, what we're going to recognize is that we go back to the form where we had it in for the quadratic formula. All right, that's our standard form. And now we're looking at functions, so instead of y equals, what do you see?
F of x.
F of x, right? A function of x. Now, function of x, f of x, is a generic term. What would you write for a cost function? What might you call a cost function if the cost is a function of the amount of items you produce? You probably wouldn't call it f of x. What would you make the function title? Give me other variables to use. F of c, so a function of cost. Okay, but that would mean cost would be the independent variable. I said that you want to find a cost of something as a function of the amount of items produced. So think about it that way.
F of p.
Not f of p, that would be, a function of, what does p stand for then? Product, okay. Halfway there I'd say, f of p. I would probably change f to something else. What would you change f to? You're trying to find the what?
Amount.
What was the first thing I said? You're trying to find the blank as a function of items produced. You're trying to find the... So what would you use? C of p or C of n. Well, you want to indicate for these functions, you're going to see them change. Usually it's the first letter of the word that you're going for. So I'm just trying to give you like everyday common terms. So if you're looking for, for example, the fluxural rigidity of a beam in engineering, okay, you want to look at the y displacement as a function of x. There you would actually say y of x as it changes. Or maybe you're looking at the force as a function of distance. So for force, it would be a capital F as a function of distance. So it looks like f of x, but this is referring to force here now. So depending on the application that you're going for, your variables are going to change. And then vertex form is the same thing we had for the last lesson. What's the only difference for this as opposed to vertex form when it wasn't for functions?
Is on the right side.
Yeah. K is now on the right side. K was on the left-hand side, and it was written like this. Okay, that's how it was written in vertex form, except this was replaced with the variable y. And that's what it looked like. But it's the same thing. Okay, so neither of these are new. We're just going to analyze them a little bit further. So nothing new here, just further understanding of what we can do with them. All right, let's look at our first example. Determine the vertex and axis of symmetry of the following function by transforming it into vertex form using completing the square. Using completing the square. So remember how I told a few of you, because I know some people struggled on the completing the square test, I said it's not going to go away. You need to know how to do completing the square. So let's take a look at this, and then afterward we're going to verify something. We don't even need the second part yet. So if I want to complete the square here, it's a little bit funky, right? Usually for completing the square it says 0 equals some equation. Whereas here we have f of x equals some equation, or some expression really. So in this case, if 0 were in the place of f of x, how would I go about beginning this if we were completing the square?
Divide by a. Or, yeah, divide by A.
That's-
Move C. Yeah.
I'd probably move C over first.
And then divide by A.
And then divide by A, right? Move C over and then divide by A. Would everybody agree with that? So let's move C over and then go ahead and divide by A. But f of x is not disappearing. F of x is there. It's still there. Okay, so start by moving that over. Go ahead and divide. Now, how would I go about approaching this next? It's going to be a little bit messy.
Once you find half of 4 and then square it, and that becomes a new C.
Okay, so half of 4 squared, half of 4 is 2, or negative 4 is negative 2, squared is 4. So let's add 4 to both sides. But how do I add 4 to the right-hand side, guys? Or the left-hand side? How would I do that? Any suggestions? Yeah, but how? It's f of x minus 7 all over 3. How do you add 4 to that? 7 now. I can't just put a... Because this is really 7 over 3, and this is really f of x over 3, right? You know what I'm saying? It's not really 7.
F of x minus 7 over 3, and add a plus 4.
Okay, for now, just tack on a plus 4. I'll do that for now. That works. That's a safe bet. I know. You could find a common denominator if you wanted to, but for now, I'm just going to put a plus 4 in the front. But you have to keep it separate. Again, 7 and f of x are both being divided by 3, so you cannot touch those. On the right-hand side now, Mike, what do I get on the right-hand side? What does that factor into when I'm completing the square? Yeah, very good. So I'm just going to write it like that, okay? So Mike's right, x minus 2, x minus 2. Now, on the left-hand side, though, I still have this weird-looking piece. What would you do next? What would you do next? This is one of those weird kind of questions where there's more than one approach, but one way might be easier than the other.
Multiply both sides by 3.
Yes. Multiply everything by 3. So multiply this by 3, multiply this by 3, multiply this by 3. In essence, bringing 3 back over here, really. So bringing that 3 over earlier was kind of a bit of a extra step in a sense. But I want you to recognize that, because the way we've been going over this is to move C and then divide by A. So multiply everything by 3. On the left-hand side, I get a 12. Then the 3 and the 3 here. What happens to these two 3's? Leaving f of x minus 7. And on the right-hand side, I'm just going to write it like this, like I had earlier. And I can see the 3 is now my A value. Remember for vertex form? This is my A value. This is my H value. And what can I do with negative 7 and 12?
It becomes plus 5.
Yes. So we have the following. This is vertex form. Here's vertex form. That's how we looked at this already. Now, if I want to move the 5 over, I can to get used to it being over here for the new way we're writing it, but you can leave it like this for now. So here's my question to you, because this is something that a lot of you struggle with on the test. And it was probably the easiest question on the test. You just need to memorize stuff. What is the axis of symmetry? What is the axis of symmetry?
The vertex, the y value of the vertex, is where you can like put,
Not the y value,
or the x value.
the x value.
You can
Okay.
put like points over.
So what is the x value of the vertex for this quadratic that's written in vertex form? What's the x value? Charles? 2. That's good. The equation is absolutely x equals 2 for the vertical asymptote. The value of the intercept is really 2 comma negative, vertex is 2 comma negative 5. So again, it's always x equals whatever h was. That was always the axis of symmetry. So I know that this graph already looks like this. I know that there's a vertical line here. It's imaginary, obviously. Going through x equals 2. And I know that the graph is going to be symmetric. Since 3 is positive, I know that it's going to open up. Since my intercept is 2, negative 5, I know that I'm going to be down here somewhere. There's my, sorry, I keep saying intercept. My vertex is right there. I don't know my intercepts right now. I didn't solve for them. But I do know that since this opens up, I will have 2 x-intercepts for this graph. Now, the follow-up, the first part of the question said, transform this into vertex form and come up with the axis of symmetry. So we've done that so far. What did the second part say? Scroll back up. What did the second part say? What are we trying to do here? What does it mean? I mean, you can read it, but what does it actually mean? What are we trying to do? Or how can we do the second part even? What should we do? It says to verify that the axis of symmetry, which is x equals h, could also be written as x equals negative b over 2a when it's in standard form. So how can I go about checking that this is true? What can I do here?
Plug in the numbers.
Into what numbers?
The ones that I got from the equation.
Okay, but specifically, what's b and what's a?
A is 3.
Good, and b is? Here's a.
4.
No, over here.
I'm sorry.
Yeah, negative 12, okay? So, looking at standard form, this a and b comes from standard form. So go ahead and write that now. Let's put a little area right here at the top. If you can slide this stuff down or just write it down below. So let's write it as x equals negative b, which is negative 12, all over 2a. This gives me positive 12 over 6, which is simply 2. So all that work we just did to transform into vertex form, just to get the axis of symmetry, could all be done by simply using x equals negative b over 2a. Please circle this, star it, highlight it, write it down. Needs to be memorized. Absolutely 100% needs to be memorized. The axis of symmetry when a function is in standard form. Okay, when a function is in standard form. Now, what about the vertex in standard form? What was the vertex that we had a minute ago? When we drew that quick graph I was showing you, what was the vertex? Somebody remind me? Look at your notes. What were the numbers though? What were they? Thanks, Ben. 2, negative 5. 2, negative 5. Well, here's the 2, isn't it? Right here. How do you find the y coordinate when you have the x coordinate? You plug it on into the function. So let's everybody go on the right-hand side over here, and let's do f of 2. So I have 3, and I'm going to use this function up here, remember. Here's my f of x. So plug a 2 in here, and plug a 2 in here. I'm going to have 3 times 2 squared minus 12 times 2 plus 7. 3 times 2 squared is really 3 times 4. Okay, I've got 12 minus 24 plus 7. 12 minus 24 is negative 12 plus 7, giving me negative 5. There's my coordinate. 2, right here I'm circling, negative 5 over here. Okay, as the coordinate 2, comma, negative 5. So if you want to find the write this down please. If you want to find the vertex in standard form, first find the axis of symmetry. Then plug in that coordinate, or that x value to get the coordinate. Properly written, again it looks like this. Your vertex in this problem was 2, negative 5, and your axis of symmetry was x equals 2. All right, summarized, we can write it like this. We could say that in standard form, the vertex, or in vertex form, it's h comma k. And over here it was x equals h. In standard form, it's x equals negative b over 2a. Now, how would I write that as a coordinate, though? X is clearly negative b over 2a, right? That's whatever x is. Right, see how h is here and h is here? So this coordinate is whatever the axis of symmetry is. That's correct. How do I write the y coordinate? Nice, Nina. Very good. f of whatever that is. We did f of 2 in that last problem. We got 2 as an answer here. We plugged in a 2 here, and then we did f of 2. So I'm just writing it in terms of our parameters a, b, and c instead of using just numbers. Questions on this? Because this is not an easy thing. It's not the easiest topic of the year, I know that for sure. And sometimes people have trouble understanding exactly what's going on. Did I lose anybody along the way, or was there something confusing at all? Okay, let's move on. Thank you. All right, let's look at example 2. So for example 2, we see that we're not in perfect standard form yet. We can manipulate it a little bit. But we want to find several things. We want to find the vertex, then the domain and range, and then the zeros. Okay, the zeros of a function, really remember, what are the zeros of a function, really? The what? Good, the x-intercept. Very good, man. Good memory, good vocabulary. So first, let's find the vertex. To do that, we have to do what we just did. Put it in standard form, but we're not going to leave the square. Okay, so let's find the axis of symmetry. So we get the x-coordinate of the vertex, and then we get the vertex y value. So try and find the vertex on your own first. To practice finding the vertex, you might have to rearrange things. So find the vertex first, and then we'll talk about domain and range once we know what the vertex is. Have you done this kind of stuff yet?
I think we're starting it.
Okay.
No.
Have you seen quadratics? You already.
Yeah, we did
Okay. Just curious. You've looked at parabolas?
Yeah.
Okay. So I'm going to start by rearranging it. Check your work, please. So we're going to have negative x squared plus 4x plus 3. I'm going to identify a and b. A is negative 1, b is 4. And I know that if I want to find the axis of symmetry, I use x equals negative b over 2a. So I plug in negative 4 over 2 times negative 1, giving me positive 2 for x equals. Just a coincidence that it's the same as the last one. Now, if 2 is the equation, or 2 is the vertex x value, how do I find the y value again? What do I do to find the y value now?
Plug it in.
Plug it in. Okay, plug it in, plug it in. Let's do it. So g of 2. So I've got negative, and I'm going to plug it into this one up here, the one that I rearranged. Negative of the quantity 2 squared, not negative 2 squared. Please, everybody pause for a second and look up, because this is the most common mistake for all of these. This is really saying the opposite of whatever x is squared. So you take x and you square it. What's 2 squared? And you take the opposite of that. Okay, this is not negative 2 squared. It's the opposite of 2 squared. Very important that you indicate that on your page. All right, so we get a negative 4, positive 8, positive 3 is 11 and negative 4, which is going to give us a 7. So what's my coordinate for my vertex as a result? 2, 7. That's part A. That's part A. Let's scroll back up for part B. If the vertex is 2, 7, let me draw a quick sketch of where 2, 7 is. This is what I want you to be. I want you to see this. I don't want you to actually draw this on your test. See it in your head. Then think. A in this problem is negative, isn't it? A was what in this problem? What was the A value? Negative 1. Remember in vertex form, if A was negative, what happened to the graph? It opened. And if A was positive, it opened. So it's the same thing again. A is negative here. The x squared term has a negative in front of it. That means this graph will open down. So please, folks, start by doing this. Just draw yourself a little sketch. Just a sketch. I don't care where it is. Now, again, on the test, you're thinking this. You're not even having to draw this. Now, if you want to find the domain of G, the domain is what? The domain is defined as what?
The x coordinate.
The values the x-coordinates can take on. Now, what do you notice? This graph is going to continue forever. In what directions? What direction are the arrows pointing? Give me some direction.
Left and right.
Left and right, or in your case, left and right, and then down. Would you agree with that? The graph is not going to go any higher than 2, 7, or any higher than 7. The height of the function is 7. Never going to get higher than that. And it's going down, but it's also going left and right forever. So if it's going left forever, and it's going right forever, what values can x take on? What values can x be? What values can x be? It's going left forever and right forever. Anything. All real numbers. A set of all numbers from negative infinity all the way to positive infinity. So a parabola, and you can jot this down if you want, a parabola's domain is always all real numbers. Because all parabolas follow the same trend. They go on forever, either like this or like this. But either way, it's going left and right forever. So the domain of any parabola is all real numbers. Okay, x is in the set of all real numbers. Or in interval notation, how do we write that in interval notation? From where to where? Interval notation? Nobody really?
Comma, negative infinity,
Parentheses you meant, but go ahead.
oh yeah, go ahead.
Two.
And infinity, parentheses.
Good. Okay? In interval notation. Remember, interval notation is just from what value to what value. From negative infinity all the way to infinity. That is not a coordinate. It's just writing an interval. Okay? From any number all the way to negative infinity, not including negative infinity, thus the parentheses. If I went from, like, say my domain was from, actually, let's hold off because we're writing that notation for the range. How about the range? What does the range mean for a graph? What's the range, Ryan? Okay, but mathematically, that's the range in general. If I say here's a range of numbers, you're explaining that. What is the range on a graph? The domain was all the values x could take on. And what do you notice? Where does y hit a max? Where does y hit a maximum on this graph? Where's the peak? What's the y? What's the height there? At the intercept, do you think it is? It's close, but how about the vertex? Doesn't the vertex go a little bit higher? The intercept is down here, isn't it? Isn't the vertex a little bit higher than the intercept? So we would say that the vertex is the highest, right? What's the y-coordinate for the vertex? 7. This coordinate was 2, 7, wasn't it? So we know that the range cannot exceed 7. It could be 7. It got up to 7 when it was at the vertex, but it cannot exceed 7. So y is all numbers less than or equal to 7. So we start with that. Okay, that's our range simply. Or in interval notation, all the way down to what? What's the lowest feasible or fathomable value? Negative infinity. So all the way down to negative infinity, up to where, Sabine? All the way up to? And if I want to include 7, what should I do? Instead of a parentheses, what should I put to say that 7 is also included? Yeah, bracket. Very good. Okay, remember the bracket means less than or equal to. You can never get to infinity, which is why infinity always has a parentheses. Okay, had it been up to 7 but not including 7, you would have put a parentheses there to show it doesn't include in 7, just like it doesn't really include infinity, because infinity is a theoretical concept. That's parts A, B, and C. How about part D? We want the zeros of the function. The zeros of the function, Niall told us earlier. Who else can remind us? The zeros of the function. What do we do to find the zeros of a given function? Ben, if you want to find the zeros of a function, what do? I'll give you a hint. Set the function equal to 0. That's why it's called the zeros of a function. Now, think mathematically. When you set this function equal to 0, that's like setting y equal to 0, isn't it? So, Niall told us earlier, you're really just finding the x-intercepts. So, set the function equal to 0, and therefore you're finding the x-intercepts. So, set this equal to 0. Just run through your calculator program real quick for me. Okay? Use your program for this one. You can use the quadratic formula, but for this, type in A is -1, B is 4, C is 3, hit enter, give me your x-intercepts off your calculator. Good. What do you got? Give me some like 4 decimals at least for now.
Negative 0.6457.
Okay. The other?
4.6457.
6, 4.
57.
Anybody guess why these numbers look similar? Let's see if we can really figure it out. Why do these numbers have similar decimals to them? It's not an easy question when we ask this thing. What do you got?
Since it's the axis symmetry is 2, seems like it's going right a certain amount, and then also to go left the same amount.
Really good. That's a geometrical interpretation. I was thinking differently. So think about the axis of symmetry at x equals 2, right? One of the intercepts is some distance away. The other intercept is another distance away. Those distances are the same because of symmetry, right? So take 2 and add 2.6457. Take 2 and subtract 2.6457. These are the answers. So it's 2 plus or minus 2 plus 2.6457. What do you think 0.6457 actually is? Or 2.6457 actually is? Go further. Algebraically. That was graphical interpretation. What do you think? Come on. Guys, think outside the box. What if we didn't have our quadratic formula, our quadratic calculator? What would we have to use? Okay, and look at the quadratic formula. Negative b, right? And isn't it all over 2a? So can't I just write it over 2a separately like this? Remember I did this a few times to emphasize some stuff? Look, what's this? What do you recognize? This is the... What did I just tell you to memorize?
That's symmetry.
This is the axis symmetry right here. Negative b over 2a. So this is really just 2, isn't it? Remember before we calculated the axis symmetry and we got 2 for it? 2 plus or minus some irrational quantity which happened to simplify to 2.6457. So this is really 2 plus or minus radical 7. That's what you get. So for your roots, you're getting 2 plus or minus root 7. So root 7 is really 2.6457. And if you take 2 and add that to it, you get the first one. Take 2 and subtract that from it, you get the second one. So when you notice, you're going to see this happening. When you get a decimal that is irrational looking, there's a good chance it came from a square root that was not able to be simplified. What if this had been a number like 9 instead of 7? If this number were 9.
Or the rational.
Yeah, it'd be rational. 2 plus 3, 2 minus 3. Your roots or x-intercepts would have been 5 and negative 1. So when you notice your x-intercepts look like they are rational, like they're a fraction that can be simplified, or an integer value, it meant that your discriminant was a perfect square here. So that's really what's physically happening, so you understand the concept and the connection between the two. Okay? Last part, and then we'll pause for today. Let's go to the next. Already, so this is not something that's not new to you. You saw this when we were in vertex form. And the same thing is happening again. Mike, tell me, when the discriminant, right, b squared minus 4ac, when it's negative under the radical, what kind of an answer are you going to get? And that's the red graph you're seeing. Okay, when the discriminant, b squared minus 4ac is negative, you're not going to have any real roots. They're imaginary, so you don't see any x-intercepts. When the discriminant is positive, what kind of roots do you get? When the discriminant is positive, what kind of roots do you get? Yep.
2 equal and real roots.
2 unequal real roots. Good. And that's the black graph here. showing two x-intercepts, and they're unequal, and they're real. And then the last case is when the discriminant equals 0. And notice, isn't this just the axis of symmetry here? Draw the axis of symmetry on the green graph. Draw that in. Isn't it the same thing as the x-intercept? If I give a coordinate here, give me a number. Pick a positive number, quick. 1, okay. Let's say this is a location of 1, this is 2, this is 3, okay? 1, 2, 3. The equation of this is x equals 1. Well, the intercept is 1, 0. It's not a coincidence, these are the same. When the discriminant is 0, what happens to your quadratic formula? What happens to this entire thing when the discriminant is 0? It goes to 0, because this is 0. When the discriminant is 0, it means this is 0. If that's 0, this whole thing is 0. So it turns out that the quadratic formula results in one answer, which is the same thing as the axis of symmetry. It's not just a coincidence there. There's a correlation. We're going to pause there. All right, so we're going to look now at that idea of min and maxes, and we're going to call them extrema. Extrema meaning the extremes. So we're looking at the highest value or the lowest value. So if we look at a function that has a greater than 0, such as the first graph here, we clearly can see that there's going to be a minimum value, because if the graph opens up, it has a lowest point on the graph. And that lowest point is indicated right here on the actual graph. And the opposite is also true. If a is negative, and therefore the graph is concave down, or it opens down, it has a maximum value. All right? Now, there's a term here and here, and you're going to have to value. Nick, have you done optimization in Calc yet?
Yes.
Okay. In optimization, imagine you have a cost function, right? What is your goal usually? To minimize or maximize the cost it takes you to make an object?
Minimize.
Minimize. So in that case, you would say, for how many, what do you want to pick an object? Something that you might imagine, cars. For how many cars, or how many cars would you want to produce to obtain the minimum cost? So the number of cars in this topic would be your x coordinate. And what would be the y value? Nick can help us if we don't get it.
The cost.
The cost itself, yeah. So when you say you're looking for the value of the extremum, or if you're looking for the value of the minimum, you're looking for the cost in that scenario. Now, you might look at another scenario where you want to, I don't know, let's see. You want to maximize surface area. Right? Why might you want to maximize surface area? In some object you're building, forget whatever it is, but when would you maximize surface area? Think of an application where you want a lot of surface contact. Come on, you gotta be able to think of something.
A sail.
What's that?
A sail.
A sail, that's great, great. So think about a sailboat. If you want more of the wind to be pushing the boat to catch more of the wind, that's what you'd call it, catching the wind, you'd want it to have a greater surface area, right? What else? What else would you want a greater surface area?
Hitting a baseball.
Hitting a baseball? Okay. You'd want to hit it like smack in the center of the bat. That might be more of a sweet spot, but the idea is similar, okay? What else? Think about when you walk to school in the wintertime. What do you put on usually? Hey, you put on boots. Boots have usually more surface area on the bottom of them, which allow your body weight to be displaced over a greater area, lowering the pressure per square unit. So if you're looking at trying to get more grip when you're walking or stay on top of the snow, if you've ever seen someone wear snowshoes, right? You ever see snowshoes, real snowshoes? They're big, and you literally walk on top of the snow. That's how people that live up in in Canada and Alaska will get around at certain times of the year. They'll put on snowshoes and they'll walk on top of the snow because there's a lot of surface area. So anyway, the idea is that you might want to minimize or maximize something. In the case of surface area, since you're maximizing the surface area, the value on the y-axis would be like your inches squared, right? It would be the actual surface area. That would be the y value. The x value might be something like the amount of material that you're using. You're trying to maximize the surface area without using too much material, or based on the amount of material you have to use. So what's important is that the y value, the y value is the value of the function. So for example here, what's that location that I just circled right there? What's the coordinate going to be listed as? Luca?
I think it's 1, 4.
All right, so if you were asked, what is the maximum value of this function? The answer is just 4. Again, terminology is extremely important, so you have to make sure you either write this down or you definitely get what I'm saying right now. The maximum value is 4. The location of the maximum value is -1. Okay, again, the max value would be 4. The location where the max value occurs is -1. Now, you might also do this with velocity time graphs. And you want to find the maximum velocity. That's a function of time. So, it would be the time it occurs is the x-axis, and the actual velocity is the value on the y-axis. So considering this, because you're going to be applying all these topics, they're all going to be applied to word problems. So you need to start thinking about that again. The fact that your terminology is extremely important so you know what you're being asked. Let's take a look at example 3. Somebody give me not a guess, but an idea or a method of solving example 3. And I think you could probably come up with it without me actually stepping you through. How might you figure out example 3? Take a minute and think about it. How might you figure out how to determine the maximum value and its location? I mean, if you are struggling to think about it, you can definitely graph it and look at it for a second to get an idea. But this will definitely be a kind of problem in the test where you're not going to be able to use a calculator to do it. All right, so for now, if you want to check to see what you would do, maybe look at the graph. Charles, I saw your hand go up. You have an idea? You want to start us?
The maximum one probably the vertex.
Okay, good. So really what we're looking for is the vertex. That's the first starting point. So let's write that the max or min is the vertex. Absolutely. Okay, that's good to know. It's got to be the vertex, because the vertex, right, is where it turns around. And either it turns around and becomes a min, or it turns around and becomes a max. What else? How would I find a vertex then? And that's just finding a max or a min. How did we find the vertex last class? We did one of these examples. And I'd rather not use completing the square. We could do that and put it into vertex form, but that's a lot of work. In the last class, we came up with another way to do it. We came up with a way to determine.
Negative b over 2a?
Yeah, what would that do for us, Cal?
That would give you the x value.
Yeah, the x value. Remember, this is the axis of symmetry. And as a result from this, we get the x value of the vertex. This is always the x value of the vertex. Always, 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 always. This is like your h value, really. So let's figure it out. Negative b over 2a is negative 8 over 2 times 4. So it's negative 8 over 8, which is just negative 1. So if that's the axis of symmetry, and we look at a graph, right? And we look at a graph. Let's draw a quick graph before we go any further up here. We know that it's going to be right here. The axis of symmetry is going to go through negative 1. So if the vertex is somewhere on here, maybe the vertex is up here. Maybe the vertex is here. Maybe it's here. Maybe it's here. It could be anywhere along this. So how do I know what the height is of the vertex? How do I figure out the height?
Find out if it opens up or down.
Okay, does it open up or down? That'll tell me whether it's a max or min, I agree. But how do I actually find the location or the height? We have the location right now. The location is negative 1. How do I find the value of the max or min?
Plug in negative 1 to the original.
Plug negative 1 into the original function, right? Let's do f of negative 1 now to get the y coordinate. And we're going to look at whether a is negative or positive now. We will. That'll tell us whether it's a max or min though, right? It doesn't actually give me the height. So we want to figure out the height. So let's go ahead and do f of negative 1 to get the y value. Remember, when you plug in the x value, what you're getting is the height of the function, or the value of the function, or really just the y coordinate. So when I plug this in, I get negative 5. Agreed? We're going to have 4 times negative 1 squared. plus 8 times negative 1 minus 1, and it's going to give us negative 5. Therefore, my coordinate is negative 1, negative 5. Niall, is it a max or is it a min? Min? How come?
Because A is negative.
Because A is negative. I think A is positive. Be careful. But it is still a min, actually. You were right the first half. Remember, A is positive, it opens up. So it's a min. You're right with the min part, but it's because it opens up, not down. Okay, if A were negative, it would look like this. It would be a max. So we clearly know that it's at negative 1, negative 5. That's probably this bottom one I drew. So I'm going to go from there. All right? So it's got to look something like this. I'm going to call this negative 1, negative 5 as a coordinate. Maybe this is like 1, 2, 3, 4, 5. Okay? So we have an idea of the graph already. Do you see how this works? So you're able to find the axis of symmetry and then go right into finding the vertex, classifying it as a minimum or a maximum. So this problem said determine the min or max value and the location. So let's write some notes real quick. This is the location. And this is the min value. Okay, we have the location and we have the min value. Together, again, they make up the actual vertex. Make sense? Okay, it's a really important topic. You have to be able to find mins and maxes, whether it be x to the third, x to the fourth, you're going to learn about more next year, and, well, more actually junior and senior year about those functions. But the idea is the same. You're still trying to find a min or a max relative to the points around it. Okay? All right. Questions. Let's look at this next one, which is a little bit more difficult here. You're definitely going to have to think back on what you learned earlier in the year to complete this next problem. You cannot do this one without it. So, for the following function, you're given a y-intercept of 7, and you're given 2 points. And your goal is to figure out what that function is. Take a minute. Maybe even actually work with the person next to you. This is not easy at all. I want to see if anybody can come up with how to do this. Again, you're given the y-intercept and 2 other points, and as a result, you need to figure out what is A, what is B, what is C. Come up with those three constant coefficients that would give you a graph containing those 2 points and a y-intercept of 0, 7. I'll take a look and give you an idea if you're on the right track, sure. No? Good idea, though. I like the idea. Keep trying other stuff, Kelly. Guys, you're not going to get this right on the first one. So try something. Let me know what you think it might be, what you have to work on it. Now let's take a look. Keep going with that. Keep going with that. You use 1 quarter, right?
Yeah.
Okay, you got 2 more still?
Okay.
Keep going. Very good. Think about using the coordinates. How could you use the coordinates? What can you do with coordinates? Where can you place them? You can definitely start by, if you want to put them on a graph and look at what it looks like. That might help. But what can you do with coordinates and a function? What can you do with x and y? Where can you place them? I'll give you a hint. The hint would be, how would you check that your x and y values are correct if you solve an equation? What do you do? Plug them in, don't you? So think that as your hint. Think about what you can do with these coordinates to check that they satisfy the equation. Only one thing you can do to check that they're true. You have 3 coordinates here, remember. So you can do this thing I'm talking about 3 times. What am I gonna do? Go back to chapter like 3. On the right track? You got more to go, right? What was I telling you? 3 coordinates, right? 2 there, and we have the y-intercept. And what can we do? This is x, and this is y, right? So we have options. We have x there, y, and we can take those and put them there, and we can see what the results. We put more than once. Good, how can we solve this?
Well, if you gotta get into subtract.
Yeah.
You, is that the?
Yes, that's exactly right. So do that, you need to do that 3 times, right? Yeah, that's the word, good word. There you go. So plug in 10, right? Now, here, for like 3 goes into max, doesn't it? And you
Oh,
can
yeah.
see everything, right?
Yeah.
Well, I was on the right track, how are we doing? Yeah, 3 times, right? So we have this equation here, this function. That's the x coordinate, that's the y coordinate. So negative 2 can go for x. And 25 can go for y. For y's. That would be line A, B, and C, right? So you have 3 variables on the y line. And you can do this with points 3 times, right? You get the 3 equations, and that's what you're going to do matrix. Close. So what I would say is first, use 3, right? Because you're using 1. So f of x is y, right? Using 10 goes into f of x. And then this 3 goes into x. So 3 squared is what? 9. So this should say 10 equals 9a plus 3c. That's one of the coordinates, right? Yeah. If you do that 3 times, you'll get a resulting thing that you can solve. Good. Now, let me just take that 0. Is that a b right there? Is that what it says? Okay. Now, once you plug in, can you do that? Yeah, once you plug in this first line right here, don't manipulate this. Do it again with the other coordinates. So erase the stuff you did after the first line. The first line is good. So do this with the other coordinates. Like see over here, 3 squared, place move that 9. Do that with the other 2 coordinates. 10 and 0, 27. And when we get it, we get 3 equations, right? How many variables do we have this? How many variables are unknown there? 3. The equation of the variables, the matrix, right? Alright, so you put the 3 in, here's a 7. Oh, because you still have 7 is the minus, so that's fine, that works. So you have this and this right now, right? Now, what was equal f of x? It isn't f of x, but it's y. So shouldn't this one equal 10? Then you plug a 3 in, that one? Now that came from, you plug 3 in. So shouldn't this equal f of x, which is 10? And then you plug negative 2 in, then you get this. Shouldn't that equal 25? And then you'll have 2 equations, 2 unknowns, because you recognize the line intercept part makes it easier. Everyone else can have 3 equations. Good. Good. Now, guys, obviously the third equation, when you plug in for the y-intercept, is going to say what? Did anybody plug in 0, 7 yet? You're going to get c equals 7 for that last one? Think about it. Plug in 0, 7, you get c equals 7. So you can already put a 7 in for c everywhere. And you can make it 2 equations with 2 variables instead. Make it a reduced matrix. All right. So let's, at this point, I'm going to put up the work to do this because I think a lot of you got the idea. So if points are contained by a curve, it means they satisfy the function. So you literally just plug them in. When in doubt, plug them in. So I'm going to start by plugging in 3, 10. Sorry. I get 10 for y, and I have a times 3 squared plus b times 3 plus c. Then I plug in 25. I have a times negative 2 squared plus b times negative 2 plus c. And then finally, this is really 0, 7. So I plug in 7 equals a times 0 squared plus b times 0 plus c. Now, obviously, at this point in time, I would probably just move these 3 constants on the left-hand side over to here and put it right into a matrix. But obviously, c is 7. so you can make it easier. All right, if you want to do that with the third one, these cancel, they're zeros, so C is clearly 7. And if C is 7, you can replace these with 7 and just move them over. So now you'd only have 2 equations and 2 unknowns for A and B, and you would solve this via a matrix. I mean, you could do it obviously with substitution elimination also. So moving it over, you would get from the first equation 3 equals 9a plus 3b. And the second equation, you get 18 equals 4a minus 2b. Again, this is the first equation, that's the second one. So I'm just altering them slightly. All right, and that comes from, again, moving the 7 over here and here. And when you write it as a matrix, again, write it with these 3 on the right-hand side of the equation. So your matrix would look like this: 9, 3, 3, 4, negative 2, 18. Okay, write it with the equal sign on the right-hand side always. Your goal is to get 1, 0, 0, 1 here, and then your answers right here for A and B. If you forgot how to do this, this was something we did in chapter 3, and I also put a video on, it's either videos from class or documents and handouts, but there's a video link that actually says practicing with the matrix or inserting matrix. So if you just open Moodle, open those little tabs and press Control F, just type in matrix, it'll pull up that one right away. So when you reduce this matrix, what you get as a result is 1, 0, 0, 1, 2, negative 5. And what that means to me, anybody? What does that mean to me? Kelly?
A equals 1, B equals 1, and
A equals,
does A equal like 1 or something?
not 1. Somebody help her out.
A is 2.
A is 2,
B is -5.
and B is negative 5. Remember, this physically tells me 1A plus 0B equals 2. This tells me 0A plus 1B equals negative 5. Remember that these are just coefficients, right? Isn't that what they are? This is a coefficient matrix. You always write in the coefficient matrix. So the first equation, 1A plus 0B equals 2, just really says A equals 2. And the second one really says B equals negative 5. And earlier we had C equals 7. So what's your answer? How do I write this all as one statement? Niall? How do I write the final function out? If I have A, B, and C now?
2x squared minus 5x minus 7, or plus 7.
Plus 7, good. Okay? Now, if you really weren't sure that you were right, you could actually plug in those points into this to check that it is true. But since you use a matrix and you did your work right, you hope to be right. Okay, if you want to come see me to go over how to use a matrix if you forgot, okay, you can do that, but I'd recommend just watch the video for like 3 minutes first. If it doesn't make sense, just come ask me. Okay, but you need to advocate. So if you don't know how to do this, you need to do it tonight. Don't say, I'm going to wait till the night before the test, and then the morning of the test, I'm frantically trying to find someone to tell you how to do it. Because this is something you should be able to do. Come up with a function given 3 points. All right? It's a good technique to learn how to use. All right, let's look at this next one. This one I find really interesting. For those of you that can really think outside the box, I think you'll find this one fun. Make up your own quadratic function in standard form for the following sketch and discuss mathematically why you chose those values for A, B, and C. So I'm going to ask you for input. We'll do this together as a class. I'm not going to give any answers. I want you to give me input. What's something you know from looking at this graph? Give me a piece of information. Doesn't have to be something about A, B, and C, but give me something about the graph that we can draw more conclusions about.
There's 2 real distinct roots.
Okay, so therefore, what can I write?
The discriminant is positive.
Good. Well done, Niall. Okay, so that part we know already. That is absolutely true. What else? It opens down. Therefore?
Negative.
What is negative?
A is negative.
Good. That is true as well. So let's write this on the side if we don't know, right? So 2 real, distinct, let's see, distinct zeros or roots. And opens down. Next.
It's shifted to the left.
It's shifted to the left. Good. So what does that tell us?
That H is positive.
Now we're doing it in standard form though,
Uh,
not in vertex form. But that would be true. But you can go with what you were saying still. So Kelly said H is going to be positive because it's shifted to the left. Well, we're not looking in vertex form. We're looking in standard form. The shift to the left does tell us something.
So negative b over 2a is negative.
Is negative. The axis of symmetry is on the left side, isn't it? So this quantity has to be negative. For sure. Again, because the axis goes through the left-hand side. What else? Give me another piece of info. There's something else I see. One more thing. This is the toughest one.
It shifted up.
No, there's not, I mean, that is true, but it doesn't have to do with that. There's one other piece of info.
It's in the max.
It's a max, but we got that already from this. Opens down. I should put the notes here, right? Axis of symmetry is negative.
Would A be a fraction for this y?
We don't really know that. You're just saying from the looks. Nina, right? We don't have numbers, so we don't know that. But I get the idea.
There's two different intercepts.
What?
There's two different x-intercepts.
Already got that, right here. Two real distinct zeros.
C is negative.
C is negative. In the last problem, wasn't C just the y-intercept? Let's write this down, please. C is the y-intercept. So therefore, C is negative in this problem. C is the value of the y-intercept. Very good, Luca. That's the last piece. And we only discovered that in the last problem, right? We didn't really discover that until just now. All right. So as a result of these four things, think about this tonight. Try